can see, it is available. Please have your microphone, camera turned off. This way saves the bandwidth for this presentation. And any question answers, I did not set up the Q&A feature, but the chat feature is active. So please use the chat feature for question and answers. You can write it throughout the presentation, and at the end, I'll have Pedram answer your questions for you. Stay up to date with our events. You can use our website, seiphilly.org. You can email us at phillysei@gmail.com, or we just started our LinkedIn page this year, so always check out our LinkedIn page, and you can use this QR code right there with the fancy dinosaur T-Rex in there that'll take you right to our LinkedIn page, and we'll definitely be using that a lot more throughout the year to keep you up to date with the different events that we're having. So speaking events, after today, our next one, it will be another virtual event. It's going to be on the Philly scoreboard expansion, which for all you local people here, it's going to be an exciting presentation. Looking forward to that one. And then because we have switched over to virtual meetings, we still want to keep that social aspect. So we, in January, look out for an event. We'll be doing a winter social. This way we can get, everybody together and still have that social aspect. We can talk, network, and just basically get together outside of work. And then our next meeting, it will be a joint meeting with GVGI, just like we do every year. This will be an in-person meeting in February. So if you're in the area, look out for that. And then our college event, we did it last year at Temple. We'll be doing it this year at Swarthmore. It's a panel. It's actually a really good time to see the students. It's all the students in our 5 area colleges are invited. It will be hosted by Swarthmore, and it's a good opportunity for the students to ask questions and listen to a panel. We had a really good panel last year, and we'll be looking to have a good panel. And if anybody's interested in sitting on the panel for the students, reach out to us, let us know that you have interest, and we'll definitely get you on board. So today's speaker, it was a great opportunity to have Pedram come and present to you. Pedram is a PhD candidate at Drexel. He started his studies in 23, and his endeavors dedicated automating the visual inspection process for structures. So he has a journal paper that was published, and he's done a lot of work on this, and I will basically hand it over to him to, go into today's presentation. So I will stop sharing, and Pedram, I will let you share. And again, I appreciate you taking your time and presenting to us today.
Thank you, Mike, for the introduction. Can you hear me and see my screen?
Yes.
Awesome. All right. Let me also turn on the pointer. So, hello, everyone. Let's start without further ado. First, I'd like to thank for the financial and resource support that I've got during my PhD. First one is from the American Society of Civil Engineers, ASCE, and Structural Engineering Institute for the Amman Research Fellowship in Structural Engineering. The second one is from the American Society of Non-Destructive Testing for the ASNT Foundation Fellowship. And I'd also like to thank for the University Research Computing Facility at Drexel University and Texas Advanced Computing Center at the University of Texas at Austin for providing GPU resources. The outline that I'm going to cover first, I'm going to talk about the problem statement, the significance and motivation behind the problem that we try to approach, the novelty about how we try to solve this problem, the research objectives that we define throughout the project, and then I'm gonna start talking about all these 4 objectives that I have: AI-based crack pattern generation, crack to graph, conversion, crack pattern-based long plasticity modeling, and also distributed plasticity finite element model. And I would wrap up the presentation with the conclusion section. So problem statement. First, I would like to talk about what is actually a shear wall. Most of you know that. We have different structural elements which have concrete shear walls. Of course, they cannot take tension, so we reinforce them. And if we look at these layout for our reinforced concrete shear walls, they're supposed to take lateral loads that push these structural elements toward left or right, and these cause to have different crack patterns on the surface of these structural elements. Once they are put into testing, we usually plot the results with base shear versus the top displacement, and here we see different cycles of the test. We load the structure, unload it, and load it to the other side, and then unload it again. Each of these crack patterns that you're seeing here at this GIF is coming from an image after one full loading cycle. So after one full loading cycle, we stop the test, we take an image, draw the crack patterns, and then we continue the test. This blue lines would give us the hysteresis loops of the test, and if we connect all these peak strengths, it would give us this green line. We call it backbone curve. There is an idea. I'm trying to set these terms because I'm gonna use them throughout the presentation. So there is a guideline by ASC 41. I'm gonna talk about ASC 41 as well. They suggest a way to convert this backbone curve to the idealized force displacement curve. So for that, we have to find Vy, which is the shear force at which the first longitudinal rebar yields, which would be usually these folks that are at the far end of each side of the wall. And then if we connect from 0 to 0.6 times Vy, we would be able to get the initial stiffness of the wall. With that, the main research question that we want to focus here is how surface crack patterns can be incorporated into as damage modeling of RC shear walls to establish a framework for post-hazard assessment in multi-hazard scenarios. There are different elements in this research question, and I would like to walk you through visually. So we have a structure and we have the shear wall, and it experiences hazard number 1. With that, we get to this stage that some crack patterns is developed on the surface of the wall, and then we try to make a performance assessment. And this is the current modeling methods that we have. We do the as design modeling. We perform the analysis of hazard 1, and we then do the assessment. But what if we have a second hazard? So as you can see, the crack patterns also develops. And the issue is that this method is not designed to proceed further. But our focus is that we do the as damage modeling of the concrete shear wall at the various stage that we're seeing here. So to do that, we want to convert the crack patterns into graph representation. And based on that, we would like to analyze the structure from the second hazard. Now that we know the problem statement, let's go to the significance and motivation behind the problem statement. There are two major motivations behind this research. The first one is the increasing frequency and intensity of natural hazard events due to climate change combined with the risk of multi-hazard scenarios. So the first one is the increasing trend in induced seismicity. And the second ones, some climate change mitigation measures have seismic side effects, such as geothermal energy harvesting and CO2 injection into the ground. Specifically in the region of Pennsylvania, we have high activity due to these uh, seismic events, which is produced by usually people, and they try. That's the reason we call them induced seismicity. One of them is really known for fracking. The third one is that climate change exacerbates the severity of cascading natural hazards following an earthquake, such as the tsunami. And the last one, uh, climate change may increase the number of natural earthquakes through mechanisms like drought-driven changes in lake water levels or alterations in glacier volumes. The last one is not proven yet, but researchers trying to investigate the idea because they believe due to global warming, the glaciers are melting down, and this change in the balance in the mass volumes throughout the Earth may cause some earthquakes. A few months ago, if you remember, we had an earthquake in Philadelphia, and it was really rare. And I was watching the news. It was rare to the point that the news was defining what an earthquake actually is to the people. And if you wonder what does a 4.8 magnitude earthquake look like, 4 to 4.9 magnitude earthquake typically has a maximum modified Mercalli intensity of 4 to 5. And usually the description corresponds to the things that I have written here. What captured my attention was that walls make cracking sound. And specifically in Philadelphia area, wind load dominates, and it is not a high load. And the structures are not designed for seismic activities. And these descriptions are for the situations that the structures are designed for seismic activities. So it is something that we should be noticing for future events. And the second motivation is the significant gap in current building codes and guidelines when it comes to assessing the performance of structures that have already sustained damage from one hazard and are subsequently exposed to another. So this is ASCE 41-23 that I mentioned earlier. It is developed for seismic evaluation and retrofit of existing buildings. We have the same name for the SEI version, which has a weird name, ACI code 369.1-22. And the last one is from the Applied Technology Council. It is FEMA reports from FEMA reports 306 and 307. But what do we mean by there is a gap in the performance assessment? I would like you to notice the first column here that we have, which corresponds to the structural components. And the issue is that these codes, they say if you see walls are cracked, just reduce the capacity by 75%. And if you see something else, or 0.5, 0.3, 0.4, and it's just giving one number. There's no description about it. And we want to know how many cracks, what type of crack, does the length of the crack matter? Does the orientation matter? But these are not presented in the ASCE 41. So we don't know what to do. And actually reducing the capacity of the walls by 75%, I think this is really conservative. So here ACI refers to ASCE. These two tables are very the same. And all these two refers to FEMA 306 and 307, which is really old. It is for 25 years ago. And we're talking this matter in 2024. So what actually FEMA 306 considers? So it considers multi-hazard scenarios. It presents a rough idea about successive hazards. They had an idea 25 years ago that we have a wall, it goes under one damage, it develops some crack patterns, and we want to perform some assessment for after the second hazard. And they compared the specimen A and specimen B. For a specimen B, there is only one hazard. So we want to be able to compare these two events. So I think there was a generation of researchers focused on seismicity back then. Maybe they knew the issues, but they faced some limitations. So and after 25 years, probably they are retired right now. And 25 years ago, there were limited tests, and therefore they only had the rough idea to present it, but they couldn't move forward probably. Another thing is that probably computational tools were not available like today. So we have access to high performance computing systems, and it wasn't available back then. And even if it was, probably it was for military usage. The last one is that machine learnings were not available back then. So even machine learning goes back to 5-10 years ago. And also that test data is still limited for AI and machine learning. I'm going to talk about what I mean about limited test data and why they are actually limited. So what does FEMA suggest? FEMA suggests that we can modify the idealized backbone curve that I mentioned in ASCE to represent the damaged state of their structure. So initially, they believe that if this is the blue line, the undamaged component, we should be able to define some lambda values that if we multiply these lambda values by the initial stiffness or initial strength, we should be able to get the damaged state of, we should get to the damaged state of the component. But what actually we see in the FEMA 306, this is why I'm calling it a rough idea, and it was not developed further. So I grade this part because I just want you to focus on the other parts. But there is still the issue is still there. It's only giving us just one number, and what is that number is actually coming from? So again, it is 0.9, 0.8, and it is basically saying that if the typical appearance of the crack pattern is something like that, choose those numbers, and it is pretty subjective. One person might think this is close to this one. One person might think the actual crack pattern that they're seeing is close to this one. Another issue is that here it mentions crack widths typically do not exceed a quarter of an inch. But another issue is that crack width closes under cyclic load. If you look at this video, you can see under cyclic load, the width of the crack closes. So it's not a reliable measurement here. But the question here is that how can we tell which crack pattern is more critical? Is it this one more critical, this one, or this one? What is the difference between them? Which one is worse? So I can say there was no systematic way to quantify the crack patterns to differentiate between them. So this is one of the motivations of this presentation. Now, what is the novelty about our approach? So the first one, we want to, it presents the first novelty. It's a fundamental shift from traditional as damaged structural models to a novel as, from as designed structural models to a novel as damaged approach. The second one is the integration of multi-hazard scenarios into the modeling framework. Third is development of computationally efficient crack pattern-based lump plasticity models. I would like to highlight the computationally efficient part. I'm going to refer to it in the conclusion section. And the last one is incorporating state-of-the-art generative artificial intelligence to enhance the data set of surface crack patterns. With that, let's move to the research objectives. So we have the experimental data that I showed you in part in the first slide, that we had the hysteresis loops and the crack patterns. We have that for several tests that have been performed in the US. We would like to first expand this data set by using AI, and then we would like to convert the crack patterns into their graph representation and use that graph features to be able to predict the reduction factors for the stiffness and modify the long plasticity modeling. At the other side of the branch, we would like to simultaneously develop the distributed plasticity modeling. This would give us the superiority to compare the results from the finite element here that we see very detailed, and compare it with the long plasticity modeling, which is a little bit simplified. Now, the first objective, AI-based crack pattern generation. So here we used denoising diffusion probabilistic modeling, which was presented 4 or 5 years ago in 2020 by Ho and his colleagues. So the idea is that if we have an image of a crack pattern, and if we add noise to this image gradually until we get to the point that it is pure Gaussian noise, which is usually done in very gradual steps, like 1,000 steps, we should be able to train models that we can give these images and denoise back the images step by step until we get to the initial image. So I have a video. It is showing the concept with the sunset image, but this shows the idea behind. So as you saw, the video started with pure noise, and then it got to this sunset. So the idea is the same here developed. What we did to train the model, it took about 10 days to train the model and about 2 weeks to generate 10,000 crack images. You can see original crack images that we fed to the model here, and then some AI-generated crack images, pretty much similar to these original crack images. If you've worked with ChatGPT, DALL-E, the idea is pretty much the same, that can generate images for us. So if you wonder how does the model generate crack images, so the idea is that once the model learns how to go from pure noise to the original image, if we give the model random images, random noises of actually random Gaussian noises, it would eventually be able to denoise the image until it generates new images for us. So with the first objective, there are 3 tasks. And for the first task, we wanted to see the feasibility of this generation. So we generated 64 by 64 patches of images. That's why you saw the images you saw were really small. And we have an under review journal paper with this task. The second one is that we want to generate higher quality images of patches 128 by 128, which is essentially 4 times the images we generated before. And it is really resource intensive once you want to generate images with higher quality. And at the end, we want to be able to connect these patches so that we have the full crack pattern of the image. The second objective here is the crack to graph conversion. But before that, what is a graph? Graph is mathematically defined as a set of nodes, these green dots that you see here, and a set of lines connecting the nodes together, which we call them edges. That would be these red lines. And next question is why we use graph. So the first one is that it is based on mathematics, so it would be unbiased. If you remember, we talked about the subjectivity of understanding different crack patterns. So mathematics gives us this benefit that it would be unbiased and it can objectively compare these crack patterns with each other. Second one is that graphs are the building blocks of AI, and it would enable us for automatic and systematic analysis. With this, we would be able to assign numbers to these crack patterns, which is called crack pattern quantification. Essentially, we're converting something qualitative to something quantitative. This way, we will have a way to tell which crack pattern is more critical or which one is worse. When we started our actually my PhD, these two was the major motivation for us. We wanted to have something that is objective and has a high automation capacity so that we can do it systematically. But after doing that, we asked ourselves, now what? It seemed that we have a piece of puzzle that it is disconnected with the other parts. This way, we started to search in the literature, and we found that we have an increasing trend in the multi-hazard scenarios due to climate change, and at the same time there is a significant gap in the standards and guidelines that we use. So this major motivation that was our initial motivation became a minor motivation, and then we followed those two motivations that I outlined earlier. The crack to graph conversion has two sides of the story. Now, I would like to start with the graph side in the beginning. So this is an image of the shear walls that that goes under test in the laboratory, and you can see crack patterns developed on the surface. So what we do, we sketch these crack patterns at the beginning, and then we use corner detection algorithms. I specifically used Shitomasi algorithm to find the starting point, crossing point, end point of these crack patterns, and we mark them with these green dots. These would be our nodes. Now the idea is to connect these nodes together based on the crack patterns. So we developed another algorithm to connect these corners together. We call them corner connection. So here it visualizes the idea. For example, node number 2 and node number 6 should be connected to each other because there is a crack pattern connecting these two together. But nodes number 2 or 3 shouldn't be connecting to 1 because there isn't a crack pattern. If we follow this guideline, we can see that the crack pattern that we had initially here is now converted to its representative graph. Now that we have the graph, we would like to extract graph features to assign those numbers that I mentioned to the graph representation. So imagine this is a network. This is a graph that we have. This is how we calculate the graph features. For each node, we count the number of edges being connected to that, and we give a node number to these nodes. We call these numbers node degrees. For example, here we have 3 edges coming to this node, so its node degree is 3, this one is 2, and this one is 4. We would like to average one of the features that we use here is called average degree of network, which is simply averaging these numbers out. And with that, we get this plot. As you remember, for each of the load steps that we had, we stopped the test, we had the crack pattern. And if we convert the crack pattern into graph and calculate the average degree of network, it would give us this point on the curve. The second one I would like to mention, the second feature, is that, for example, we have this crack length. Imagine these red numbers are showing the length of these cracks. The weighted degree of the network would be the average of these two numbers. For example, for this node, that would give us 98, specifically for this node. And then if we do the same for all of the nodes, we would be able to get the weighted degree of the network. If we average those, we would get weighted average degree of the network, which would be the average of these green values. And if we plot for each of the crack patterns, we should be able to plot weighted average degree of the network versus the load steps. You can see the crack patterns are developed through the test, and it is starting from some disconnect cracks, and at the end we have very intense cracking pattern at the end of the test. And of course, these graph features have mathematical terms, mathematical equations. Now that we learned about the graph side of the story, let's move to the experimental side of the story. So these are the two shear walls that we wanted to use to test our idea. So the first one is called SW1, shear wall number 1, and shear wall number 2. These are the characteristics of the walls. If you wondered, they are called large scale tests because if you compare it with an average height of a person, it is still taller. Even if you are 7 feet tall, still these walls are taller than you. And these are really expensive tests because, and this is the reason that I was mentioning, there are limited test data back then and still now for different purposes. Even to give you an idea, the actuators that are used to push and pull the top of the wall, they are hundreds of thousands of dollars, if not millions. And only a few schools in the entire United States have the ability to do large-scale testing. This is why these test data are really precious and they are really rare. So we have here two different shear walls, and they have two different aspect ratios, which usually show the dominant behavior of the wall. If it is less than 2, usually they are considered to be shear dominant behavior, and if they are 2 or above, they're usually considered to be flexural dominant. So these are the hysteresis loops that I showed this one to you earlier. It is showing base shear versus the top displacement. If you remember, our idea, our goal was to find these lambda values that if we multiply them by the initial stiffness, we would be able to get these stiffness for the damaged state of the wall. So for that, again, I'm showing this graph. We use the idealized backbone curve. So first we have to find Vy, and then we multiply that by 0.6 Vy, and this would give us the initial stiffness. For the damaged state, one of the issues that we had throughout this project, you're hearing the success story, but we had to go back and forth between these between these guidelines, ASCE, FEMA, to define different parameters defined. So to get the stiffness of the damaged state, ASCE suggests to use the unloading slope for that purpose. So we got these slopes from the unloading slope, and it gave us the stiffness of the damaged state of the structure. And with that, we were able to calculate the lambda values for both of the walls. Now that we have saw the story from the graph perspective and from the experimental perspective, we have to marry these two worlds together. So remember that we had this crack pattern, then we converted the crack pattern into its representative graph, and we want to get some numbers to be able to convert the damaged state, the undamaged state, to the damaged state. So these are the lambda values that I showed you in the previous slide and in the table. This is the ground truth, and we use the graph features to predict these lambda values. And as you can see, we're getting a pretty good match between the ground truth and the lambda values. So it is showing us that if we look at these crack patterns, convert them to their graph representative, we would be able to tell how much should we modify this undamaged component to get to the damaged state. And this is the graph for the second shear wall that I showed you. Again, we're seeing a great match between these two shear walls. And if I want to talk about the errors, we're seeing that the errors are about 4% or 7% for each one of the walls, and the coefficient of determination is 0.98, 0.94. The more it is closer to 1, the better. And these are the equations outlined for each of the walls. So the second objective has, again, 3 tasks. Constructing and investigating the evolution of crack graphs of RC shear walls. This is the paper that Mike mentioned, and we published that. The second one is calculating reduction factors for each load step for each shear wall. And the third one is performing a regression analysis. The idea for the task 3 is that we used the crack patterns from one wall to predict the lambda values for the same wall. Now, we have this idea to be able to use to present an equation that is based on some shear walls, and we can get the lambda values for other shear walls. This way, we would be able to generalize the idea, because if we go to a real scenario, what we have is only a crack pattern, and we would like to be able to guess to calculate the lambda value for that specific scenario. Now, the third objective, crack pattern-based long plasticity model. So for this one, we used OpenSys for the long plasticity models. We used the fiber-based model with linear elastic model to model the wall, which is outlined with this black line. And then we used zero-length nonlinear spring hinges in series, and we put them in critical points that the shear wall might face some plastic deformations, and we used pinching for material to capture the nonlinear behavior of the wall. So these gray lines are again those blue lines, the hysteresis lines that I showed you before, and these blue curves are showing the results from the OpenSys that we use to capture the behavior of these models, these shear walls. So they're showing that we were able to capture the initial stiffness of the wall. We were able to capture the peak strength of the walls with maybe 5% tolerance, and with a very good we saw a very good match with the loading and unloading paths of the walls, but there were some issues with to capture the pinching effect that we have to still investigate further these ideas. Now, let's talk about the multi-hazard scenarios. So SW1, crack pattern-based lump plasticity modeling. We saw this curve on the previous slide. Now, the idea is that we have the test data, the hysteresis loop. So we want to consider until a certain cycle as the first hazard, which is grayed out here in this part, and consider the rest of the cycles as the second hazard, which would be these dark black lines. So the idea is that we see this crack pattern, and then we convert this crack pattern into some lambda values, and then we modify this blue model with those lambda values to get to these red lines here. These red lines are supposed to capture the behavior of the wall that is shown in the dark black lines. The idea here is that the wall has sustained damage after 6 cycles, and we want to be able to model the behavior of the wall from cycle 7 and until the end of the test. And remember that we didn't have any prior information regarding the what loading has been applied to the wall so far. What was the stress strain that the wall experienced? Nothing, just the crack pattern. We just looked at the crack pattern, we got the lambda values, and then we modified the model to capture the behavior of the wall. So this is one load step further. So we assume that the model has sustained 7 cycles of damage, and we modeled it from cycle number 8 until the end of the test. And this is, again, another cycle further. And as we go further, we see a better match between the black lines and the red lines. Here, from cycle 6, the 2 first cycles were not captured very well, but essentially we were able to capture the peak strength, the loading and unloading path, and the pinching also seems to be a little bit better than this blue line. We have a gap here, but here it is matching better. The same idea is here for the second shear wall. We had this test data, and we tried to get a match with the lump plasticity model. So we started from cycle number 4 to cycle number 5, 5 to 6, and 6 to 7. Again, we're seeing that we're getting a very close match with the wall just by looking at the crack pattern developed on the surface of the shear walls. Again, I would like to emphasize, we didn't have any prior information on what was the loading history that was applied to the wall. Nothing, just looking at the crack pattern, converting this crack pattern to its representative graph, and then getting the lambda values to be able to modify the backbone curve of the lump plasticity models and get a match with the rest of the wall. So here, the tasks are creating and validating crack pattern-based lump plasticity models for shear walls. The second one is benchmarking those models, the as damage models against cyclic loads. And at the end, we would like to be able to compare the as designed results that we get with the as damaged scenarios. The last objective is distributed plasticity finite element modeling. So for that, we used LS-DYNA for the distributed plasticity finite element modeling. The distributed plasticity models can capture both the geometric and material nonlinearity, and it would be more precise. And for the concrete, we used Winfried material, which is known to be the best material that has been suggested in the literature to capture the behavior of concrete. And we use an implicit solver for these models. So you're seeing the Elsteiner model for the first shear wall and for the second shear wall. So for the first shear wall, we were able to capture the, again, initial stiffness, capture the peak strength, capture the loading and loading path, but there were some issues with the pinching effect. Unfortunately, we ran into some issues for the computational resources, so I don't have the results for SW ready right now. The idea is that we use Elsteiner results to be able to compare it with the long plasticity models. Now, one issue that I would like to highlight here is that today that we're talking about this idea, still we have issues with computational software in terms of capturing the crack patterns. Here is the GIF that I showed you at the first slide, and it is actually coming from different load steps of SW1. There is no stage that you can see the crack pattern matches with the materials here at Elsteiner, although the hysteresis loops have a very good match with the actual test data. So this is a part that requires heavy investigation and research for future works. Here, our objectives is to create and validate nonlinear finite element models for RC shear walls with in Elsteiner. And then we would like to do a numerical simulation of synthetic multi-hazards. Up until now, we used the cyclic loading as the multi-hazard idea, considering from the starting point until a certain loading cycle as the first hazard and continuing the rest of the cycles as the second hazard. We would like to be able to consider until a certain load cycle as the first hazard, and maybe use actual record of earthquakes to continue the second hazard. That's why we're trying to develop these distributed plasticity modeling, because with the actual test data is limited. So with this finite element model, we would be able to verify our long plasticity models. The last task here is investigating the load displacement degradation in multi-hazard scenario that I kind of described it here. And conclusions, application of the state-of-the-art generative AI for crack image generation presented and investigated, a novel graph-based method presented for systematic and objective crack pattern quantification, a novel physics-based approach for employing quantified crack patterns into numerical models presented, a practical framework for assessing RC shear walls under multi-hazard scenarios presented. The presented approach addresses a long-lasting gap in the standards and engineering codes and guidelines. And presented crack pattern-based long plasticity modeling is suitable for rapid post-disaster assessment. This is the part that I mentioned earlier, the computationally efficient model. If you remember, a few months ago, we had a hurricane in Florida, and there is a city, Fort Myers. The city sustained 2 hurricanes in just 2 weeks. So imagine you have to do rapid post-disaster assessment in only 2 weeks, and we're talking about large scale in structures and in cities. So developing detailed detailed modeling would not be an efficient way in short amount of time. Limitation and future work. This research is only one piece of the puzzle, obviously, of the bigger picture. The presented method is for element scale, and there is an potential for this framework to be investigated in structural scale. We specifically used OpenSeas because I've seen some companies use OpenSeas to develop structural scale modeling. So the idea is to be able to scale up this framework to a structural scale. And we would like to investigate this method on other structural elements that develop crack patterns, for example, beam column concrete joints. With that, I would like to thank you for listening to this presentation, and I would take any questions.
All right, thank you, Pedram. That was very interesting. If anybody has a question, please use the chat feature. I'll actually get things started. So with your research, you're talking about post, hazard, assessment or disaster assessment. I know it's probably future research, but is there anything that you would take that information, you've come up with everything, you've determined that K value. Would that ever go into an initial design of, based on what code says to design your shear wall for that it could handle based on, historic data from the area that you are, building the structure and applying it, that it can handle certain, hazards, and that you have a little bit more confidence?
If I'm not mistaken, you're talking about maybe performance-based design that you can have, you anticipate if you want to have that much performance, you would expect probably this crack pattern, so that you should design the structure with these aspects. The best answer I can give you and the closest is that we thought about it, but we're at the initial stage, and we're at the as I mentioned, it's a piece of the puzzle of the bigger picture. The focus here on this presentation was mostly on the post-hazard assessment, that the structure has sustained some damage, and we want to know what should we do with the current structure if we see some crack. Are we gonna just fill it with some like epoxy or FRP and then leave it as that, or do we need some actual numerical modeling to be able to predict the performance of the wall?
Got it. Understood. Anybody have any questions? I don't see anything in the chat. All right. When is your time frame for defending this?
Hopefully next year around this time.
All right.
I would be able to defend the PhD thing. Yeah.
Well, good luck. I don't see anything. Well, thank you very much. I really appreciate, we really appreciate you coming on. Looking forward to seeing where we go.
Thank you very much for the invite.
Yes. So I am now sharing the screen for the PDH, and I will also put the link in there for the certificate for anybody that needs their certificate. But again, Pedram, thank you very much. I thought it was a great presentation. It's very advanced, and I'm curious to see where this goes and what we can use, how we can use this and apply it. And as a bridge person, I'm curious of outside of shear walls, pier columns and everything, is there something we could use from that aspect? Because, obviously with the bridge columns and, piers, they're more readily accessible that you can, see the cracks and how they are. So, all right. If nobody has any questions, again, thank you very much for attending. Look out for our next presentation in January on the Philly scoreboard expansion. So have a great day, everybody. And again, Pedram, thank you very much.
Thank you.